Hey guys, so I'm starting a new series talking about maths and physics and some combination of both at least at a higher level. And it is the aim to have A-level students or even first year and second year physics and math students have a greater grasp and appreciation of the physical principles and how they are underpinned by mathematics basically. So the first in these videos will be on Fermat's principle of least time. Now, Fermat's principle of least time was derived in the time where light was still thought of as a wave. So it would still be many years until the argument between light being a particle or light being a wave would have been in full effect. So Fermat's principle is can basically be categorized under the wave theory of light, and it actually follows mathematically actually from Huygens' principle, where Christopher Huygens talks about wave light being a series of waves propagating via a wavefront, and that wavefront continues to propagate due to wavelets on the wavefront, creating secondary waves. So, Fermat's principle of least time is basically a statement that light travels in straight lines and will take a path between points A and B in the least amount of time. So, light travels in straight lines, and any path that the ray of light takes between 2 points A and B will always be in the least amount of time. So what we are going to do is that we are going to use this to derive the law of reflection. And for those who have forgotten, the law of reflection, if I can get out the words, the law of reflection basically says that if I have a wave coming in with an angle of incidence I, then if it reflects off of a surface, the angle of refraction will be the exact same as the angle of incidence. So basically, the angle of incidence equals the angle of refraction. And just so that I don't confuse anyone, that stands for incidence, incidence, and R stands for refraction. So in a nutshell, this is the law of reflection. Okay, and you would have learned this in first year A-level physics. Okay, so Fermat's theory can actually derive this. It may not be signs actually. We'll soon find out that well, my method anyway doesn't include signs, but it includes causes as the trigonometric function. Anyway, let's continue. But before we first of all continue, I just want to dress up what the things that we are going to use in this particular topic, and that is we are going to use trigonometry. So we are going to use trigonometry, and we use trigonometry to study relationships between lengths and angles of triangles. So trigonometry is used to study relationships between lengths and angles of triangles. Whoops, made a slight error there. triangles. Okay. And the second thing we are going to use is that we are going to use calculus. In particular, we are going to be using differentiation. And differentiation is used to find rates of change. And it is also used to find minimum and maximum points of functions. Let me just complete that, of functions. Okay. So, to go over Fermat's principle of least time, it talks about light traveling in straight lines, and that the fact that it would take the least amount of time when traveling between two points A and B. And it directly defines the law of reflection, which is the angle of incidence equals the angle of refraction. And in order to prove this, we are going to be using trigonometry and differentiation. And I apologize for my handwriting. I'm still getting used to the pen here. My handwriting's bad anyway, but let me use that as an excuse for now. So the first thing we need to do is that we need to draw a scenario which accurately describes a ray of light reflecting off of a surface. So I'm going to draw a surface here with a normal, which I'm illustrating using the dashed line here. And in blue, I'm going to have my ray of light coming from the left. It bounces over the surface and goes to the right. And these arrows basically tell us the direction that light is coming in. Now, for convention, which is what I like to do as a physicist, I like to say that my ray of light is coming in with a speed u. So it's coming in with an initial speed, and it is leaving with a final speed v. These won't come in, these two notations won't come into play in the actual solution, but I just use it to dress up my illustration. As a physicist, I've learned that whatever I'm trying to solve, I must always draw it, and I encourage everyone else to do the same. So we are going to define some more things. We are going to define some angles, and we are going to define this angle here as the angle of refraction, and we are going to define this angle here as the angle of incidence. Furthermore, we are going to define a vertical length, and we are going to call that vertical length just B. We're just going to give it the notation B, and we are going to call on the left side, where the ray of light is coming from, we are going to call this length A. Okay, because as you can see, the light travels diagonally, so it has both a vertical component to its direction and a horizontal component to its direction. It's the total horizontal length. I'm just going to call that L. But in order to allow me to solve this problem, I need to separate the initial horizontal trajectory from the final horizontal trajectory. And I'm going to label this side X, just arbitrary. And I'm going to label this side L minus X. And mathematically, it should be such that the total length L equals X plus L minus X. Okay, very, very straightforward. Okay, so what we are going to do first of all is that we are going to write a mathematical expression for the total length, okay, the resultant length that the ray of light is traveling. And in order to do that, we need to use trigonometry. So trigonometry says that if you have a triangle with a side A and a side B and a side C, which would be the longest side, aka the hypotenuse, then trigonometry says that A squared plus B squared will equal c squared, such that c equals a squared plus b squared all root. Okay. Now, that is exactly what I'm going to do in order to solve this problem. I'm going to use, well, to at least dress up this problem, I'm going to use trigonometry. So I'm going to define a total path length P. So total path length P, where P is basically the resultant path that the light uses to traverse this picture. And I am going to use trigonometry to help me to write a mathematical expression for both of these. So the total path P is going to equal to the hypotenuse of this right angle triangle on the left, and that's simply going to be a squared plus x squared all root plus the hypotenuse of this triangle, right angle triangle on the right, and that is simply going to be L minus x all squared plus b squared all rooted. Okay, now here, this is actually a pivotal part of our solution. What we have done is that we have expressed the path that the light is taking, left to right, even as it is bouncing off of this boundary. Okay. So, how do we use trigonometry in order to solve this? Well, we are going to use differentiation. So, x. If I define my coordinates as x horizontally and y vertically, okay, I can tell myself that, oh, okay, in order to find out how this path changes, okay, in order to find out how this path changes, I am going to find the rate of change of this function with respect to x, the horizontal distance. I don't much care about the vertical distance because the scale of the vertical distance is very large, and for now we just assume that the ray of light comes from a height and bounces back to that height. We are basically slightly trivializing the problem. Okay, so we only care about this horizontal variable, the horizontal distance. Okay, so we want to find the rate of change of the path of light, and because Fermat's principle of least time says that light will travel the shortest distance in the least amount of time, we want this rate of change to actually equal to 0. Okay, and we want it to equal to 0 because whenever you set a rate of change equal to 0, you are finding what is called a minimum or maximum point. Okay, so we set rates of change to find minimum or maximum points. Okay, right, so let us continue. So right now we have our rate of change, so the change in P over the change in X, and we want to set it to 0, but P itself equals a squared x squared root plus L minus x all squared plus b squared. Okay, now this sort of differentiation, it's both a combination of chain rule and differentiation by substitution. So let's do it in two parts. Let's first of all handle the left side. So let's differentiate the left side of this addition sign. Okay. So when we differentiate that, we are going to use chain rule. So this square root is basically everything to the power of a half. So chain rule says that we can differentiate what's inside the brackets, take it outside, multiply by the power, lower the power by 1. Okay, in a nutshell. And we will find that the differential of the left side ends up equaling to x over a squared plus x squared all root. Okay. Now I will do the right side in slightly more detail, okay, because this side requires some substitution. Okay, so if you bear with me, let's follow it through. So I'm going to rewrite this in a slightly different way. And I'm going to rewrite it as L minus x squared plus b squared, everything, so big brackets, to the power of a half. Now I'm going to make a substitution that u equals L minus x, and I'm going to differentiate u with respect to x, and that's going to give me minus 1. Okay, that's going to give me minus 1. Now, in order to complete this differential, I need to relate the fact that I've made the substitution u equals L minus x, and I need to put that back in there. But before, this was with respect to dx. Because I've made the substitution u, I need to change this differential to du. Okay, so if we flip to the next page and make our necessary substitutions, we will see that at the end, what we have is u squared plus b squared to the power of a half, negative sign, du, and this is what we are differentiating, and it's a lot easier to do now. So we differentiate this, we differentiate what's in the brackets, we bring it outside, we multiply by the power, and we lower the power by 1. Okay, so step by step, I differentiate what's inside. Because b is a constant, that disappears. Because this is the variable, I multiply by the power, take 1 from the power. So outside at the moment looks like this: 2u u squared plus b squared. And then I multiply by this power, and I'm going to do it on this side. I multiply by this power, which is a half, and I take away 1 from the power. So the new power becomes minus a half. Now remember that we said that u equals L minus x. So that whole thing eventually becomes minus 1, because the half multiplied by the half is just minus 1. And we don't need to write the 1. L minus x. And then underneath, I can bring that down. That becomes L minus x all squared plus b squared to the root. Okay. So in total, dp over dx is going to equal a squared plus x squared all root x, and then minus L minus x over L minus x all squared plus b squared all rooted. Okay, now what I'm going to do is that I'm going to set that to 0. So I'm going to set it to 0, and this allows me to rearrange and rewrite this whole expression as this. I apologize for my slightly wonky handwriting. Okay, now let us refer back to our triangle. triangles that we drew in the beginning. So we have the left side triangle, a squared, x squared, and then we have root a squared plus x squared here. The right hand triangle, we have L minus x squared, we have b squared, and we have L minus x squared plus b squared all root. Okay. Now, in case you have forgotten, trigonometry says, well, let's just rewrite our trigonometric rules. Okay. Sokotoa. I prefer to say silly old Henry couldn't advance his troops over Africa. Okay. That's my favorite way to remember my trigonometric identities. Okay. So what does this equal? L minus x. Well, L minus x is relevant to the right angled triangle. And if we do everything with respect to the angle here, it all comes together. So L minus x is actually the adjacent. L minus x is the adjacent to this angle. Okay. So in red pen, I'm going to call that the adjacent. L minus x squared plus b squared all root, that happens to be the hypotenuse. Okay, this is the hypotenuse of this triangle. So I'm going to write down a h there. Now, if we come to this expression, x, what is x with respect to the angle? X with respect to the angle is the adjacent also. And you can probably guess that this on the bottom, a squared plus x squared or square rooted, is going to be the hypotenuse. Okay. The trigonometric identity that we are going to end up using is ka. Cos of the angle equals the adjacent divided by the hypotenuse. Okay. So let's rewrite these two expressions. Bearing in mind that this side refers to the angle of refraction, and this side refers to the angle of incidence. Okay, let me box those in green just so that they are well separated. Okay, so this side is actually going to be cos of the angle of refraction, and the right side ends up being cos of the angle of incidence. Now, because cos angle of r equals cos angle of I, this is basically saying that the angle of refraction equals the angle of incidence, which is the law of reflection.